Cournot Duopoly and Nash equilibrium. First, I'll explain what's Cournot Duopoly and then Nash equilibrium for this Cournot Duopoly game. And finally, I'll give you a graphical illustration of what Nash equilibrium looks like in a continuous action game. Note that this graphical illustration would be independent of the Cournot Duopoly. We consider two agents, and each agent is a firm that manufactures a certain divisible good. The action xi of each agent is the quantity produced by that agent of this divisible good, and it's a continuous quantity. So the action here can be anything between 0 through infinity. In fact, it can be 3/4 or square root of 2. That's why I say that they are manufacturing divisible goods like steel. Steel you can manufacture in any quantity, but you cannot have uh, 2.5 vehicles or square root of 2 vehicles. So vehicles are not divisible goods. They're indivisible goods. Anyways, so the action of agent I is the quantity of that divisible good that's produced by that agent. And we have two agents, 1 and 2. Therefore, I can be 1 or 2. The total quantity that's produced by both the firms, assuming there are only two firms that produce that divisible good in the market, is x1 plus x2, and we call that x. Now, from economics, the unit price of the divisible goods, like dollars per ton or uh, whatever, uh, goes down slightly as the total quantity available in the marketplace increases. This is consistent with economic theory. And so we let the unit price of this divisible good be equal to alpha minus rho x. So negative rho is the slope. When the quantity is practically 0, then this is the unit cost of the good. And as the quantity of the good, total quantity of the good in the marketplace increases, the unit cost gradually goes down like this. And we assume that it's a straight line with a slope of negative rho. So the revenue earned by agent I is the unit price times the quantity sold. So it's P times XI. Now, there is also a manufacturing cost. The manufacturing cost is proportional to the amount of the divisible good that's being produced by that agent. So it's equal to lambda I xi, where lambda is a proportionality constant. The payoff of agent I equals the revenue P times xi minus its cost minus lambda I xi. So this is the net payoff of agent I. And since we have two agents, we let I equals 1. We get this expression for the payoff of agent 1, and letting I equals 2, here we get this expression as the payoff of agent 2. So these are the expressions that we just obtained for the payoffs of agent 1 and agent 2. Once again, this alpha minus rho x1 plus x2 is the unit price of the good, and the total revenue earned is the unit price times the amount or quantity manufactured, that's X1, and this is the total revenue, and then the manufacturing cost is proportional again to the amount of divisible good produced, so we have to subtract that. This is the manufacturing cost, so this gives you the payoff. Now, let's proceed to find the best responses of the agents. For each agent I, the best response to the other agent, remember when I equals 1, then negative I equals 2, and when I equals 2, then negative I equals 1, because we only have two agents. So this is the expression, the best response of agent I when the other agent, its opponent, is playing x negative I, can be obtained by differentiating its payoff with respect to x I. So for agent 1, what we have is the payoff of agent 1 is given by this expression, and taking its derivative with respect to agent 1's action, x1, we get this, and this must be equated to 0 to get the best response. When is this equal to 0? When x1, the best response to x2, we are trying to find the best response for agent 1. So this is agent 1's action here as a function of agent 2's action. That's given by, so this is x1 equals, from this expression, we get this alpha minus lambda 1 over twice rho minus x2 over 2. In a similar manner, for the other agent, the best response of agent 2 would be, again, by differentiating this and letting it equal to 0 and solving for x2, what we get is x2 as a function of x1 is alpha minus lambda 2 over twice rho minus x1 over 2. You can observe the symmetry between the two expressions. So let's write down the best response functions of the two agents and proceed to find the Nash equilibrium. Now, this is a continuous action game because x1 and x2 are continuous quantities. So let's write down the two best response functions, br1 of x2 and br2 of x1 here, and proceed to find the Nash equilibrium. So at Nash equilibrium, we know that both agents are playing their best responses. So x1, agent 1 is playing its best response. So x1 star is equal to this expression with, since we know that x2 is, agent 2 is playing its best response, we replace x2 with x star 2 here, whence we get the expression for x star 1. In a similar manner, from this expression here, we get the expression for the Nash equilibrium action of agent 2, x star 2, which is given by this. Now, how to find x1 star and x2 star from these two expressions is by solving them simultaneously. Solving these two expressions simultaneously, we get at the values of x star 1 and x2 star at the Nash equilibrium, the continuous Nash equilibrium of this Cournot duopoly game. So these are the expressions for the Nash equilibrium actions. Now let's try to look at Nash equilibrium graphically. Note that this is a generic illustration of continuous action Nash equilibrium. It won't represent the Cournot model that we had discussed earlier. In this figure, the x and y axes are the continuous actions of agent 1 and agent 2. This is A1, the continuous action of agent 1, and this is A2, the continuous action of agent 2. And these red circles are, they represent constant values of pi 1, the payoff of agent 1. This is where the payoff of agent 1 attains a maximum, and the corresponding actions of agent 1 and agent 2 would be here for agent 1 and agent 2. Now, these contours, as I said, represent values where pi 1, the payoff of agent 1, is constant. And as we go further away from this maximum value, these contours represent decreasing values of pi 1. For instance, if the maximum is 100, then this contour here might represent 90. This contour might represent 80, payoff of 80. Everywhere in this contour, the payoff would be 70, 60, 50, 40, and 30 here. So as we go further away, the payoff decreases. But of course, agent 2 won't necessarily play this action that would maximize agent 1's payoff, because agent 2 would try to maximize its own payoff by 2, which is different. Now, let's suppose that agent 2 picks this action A2. It's represented by this dashed blue line. How would agent 1 respond? Now let's suppose agent 1 picks this action here. And the intersection of this vertical red line for A1's action and the horizontal blue line here, this intersection would determine agent 1's payoff. And this intersection, point of intersection, actually lies on this outermost contour. And if this maximum payoff is 20, if the maximum payoff is 100, 90, 80, 70, and so forth, this would be, let's say, a payoff of 20. So agent 1 would get a payoff of 20 for choosing this action. Now, this contour is for 20, and this contour is for a payoff by 1 of 30. And so if agent 1 picks this action instead, let's look at this intersection point. Maybe this represents a payoff of 27 for agent 1. Now, if agent 1 picks this as the response, then the payoff would be on this contour, which represents 30. And if agent 1 picks this as the response, we see that the payoff would reduce, and it would get lower and lower as we go further away from this point here. So this payoff, where the horizontal line, which represents A2 action, is tangential to this contour, is the point where A1 would maximize its payoff. So this is the maximum payoff for agent 1 for this action. If we go either this way, the payoff of agent 1 drops, and if we go this way, the payoff of agent 1 again would drop. So this point where a contour is tangent to the straight line is the point where agent 1 would maximize its payoff. In other words, the point where this horizontal line, which is A2's action, is tangential to one of these contours of constant payoff for agent 1 represents the best response of agent 1. So this is agent 1's best response to this value of agent 2's action. So now let's proceed and draw other horizontal lines and locate the points of tangency with the contours. Here, 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 here. So this set of points, all these points here represent best responses of agent 1 for different actions A2. And this straight line that joins all these points together is the best response curve of agent 1. So this is the best response curve of agent 1. This solid red line here. Best response of agent 1 to any action of agent 2. It is this here. Next, let's move on to the payoff of agent 2. So these contours here represent equal payoffs for agent 2, and this point here is the maximum payoff of agent 2. As we move further away from the maximum payoff, this point here, the payoff of agent 2 keeps decreasing with increasing size of the contour. If this is action 1 of agent 1, what should agent 2's best response be? There are different ways in which agent 2 could respond to agent 1's action, and each would fetch a different payoff for agent 2. This vertical line here is tangential to one of the contours at this point, and by a similar reasoning as before, this action of agent 2 represents the best response to this action of agent 1. This is the point where this vertical line is tangent to one of the contours of equal payoff of agent 2. Therefore, if we draw vertical tangents to all these contours, then the points of tangency represent best responses of agent 2 to different values of agent 1's action. And if we join all these points of tangency together, we get the best response curve of agent 2 to agent 1's actions. So this is the best response of agent 2. Now let's superimpose the best responses of agent 1 and agent 2 here. This is the point of intersection where both agent 1 and agent 2 are playing their respective best responses. Thus, this point is the Nash equilibrium because here both agent 1 and agent 2 are playing their best responses to one another, which by definition is Nash equilibrium.